quick overview here. We can take a look at what's going to be there for us. We have part 1, which deals with a few lines of code that deal with integration of function. So to have MATLAB helping us to do the integration, especially useful for functions that are not easy to integrate by pencil on a piece of paper. The second part will introductorily deal with the Michaelis-Menten rate equation. And you should be familiar with the form of the equation a little bit, but we'll see how flexibly we can deal with this equation when using MATLAB. This brings us to the core exercise here, which deals with the Hill function, a generalization of the Michaelis-Menten equation. And we'll do especially one exercise that's maybe not so straightforward to solve, and that requires a little bit of careful thought by going line by line through the corresponding MATLAB code to show you how that works. If we have time in the end, I'm going to hint at a useful database that's on the internet, available online, where to get rate constants and parameters, for example, for Hill-type equations. And we'll take a look at this, what that looks like, and I will also mention some of the dangers associated with looking into such databases. Right, that should be it as an overview. The core, as I said, of today's session will be the Hill equation. Archibald Hill, a physiologist, British physiologist, proposed this equation quite a long time ago. He was a Nobel Prize winner in medicine and physiology, and he worked as a professor of physiology for almost 30 years right here at UCL in this building where I'm transmitting now this session. So we have a look at this in a while. To get into the first section, we start with the warm-up exercise, where we look at integration. And I open my MATLAB code. This code is a slightly stretched version of the code that you can download from the materials page. And let me take my webcam off for the moment to make you more space. The GoToTraining viewer window can be expanded using the mouse in the corner, either the lower left or the lower right corner. Please try to make it as large as possible to get the best view of my windows here on my desktop. And for today's session, I might recommend, unless you are very experienced in switching between windows, to follow what I'm doing here line by line. Try to understand how it is done, and then do it yourself later and try to reproduce what we have done here. So if we start looking at integration, then we have an example here that starts by telling MATLAB that we are going to do it symbolically. It means we want a function as an output that contains all the variables that we define and that we can manipulate, for example, by rearranging, by simplifying, by differentiating, and so on. So if we want to have our function, we first define our symbolic variable, and in this case shown here, we have only one variable associated with a radius. If you remember the textbook example, one variable called r. And with this command sims, we define it as a symbolic variable for further use, the symbolic toolbox. Next thing is we have to define the function that interests us. And I have taken this function from the textbook, so you might look it up if you don't remember it, but you can just look at it now, how it's defined. We give it a name, which is nsim. And then we have, it is defined by 2 times pi times the radius. And this is multiplied with our so-called growth term or expanding term times 0.1 plus 0.002 times r. So a function that is square in r, because r times r will be r squared. If we want to integrate this function, we now have to remember its name. As I say, nsim. You can see it here highlighted. To actually perform the integration, we use the symbolic function int, short for integration, and we apply to the function that we have defined as nsim. That's our function here. And we specify the variable. This is the variable with respect to which the integration is performed. And it's as simple as this. If we now perform the code so far, we would get the output of the integration right now because we haven't suppressed it. So let me do all this code. I'm doing here an execution of the code by selected text. So if you see text highlighted in yellow, that's my selected text. And if you want to execute that, there's various ways to do it. If you right-click on your mouse, then you will have an option evaluate selection, and that's one way of doing it. And you can see, because I have not suppressed output immediately on my command window, I will see the output, and it's not surprisingly the function that is seen here. So we can then start to integrate this function, again evaluating selection, and we can then check. We have our original function squared in r, and we have our output given in a symbolic fashion, means that we have our pi and our r within this function without having specified the exact value of r. So we have an indefinite integral here. We can now use this indefinite integral for whatever purpose we would like to do. But you can see the idea. I summarize: define the symbolic variables, define the function of interest, and finally perform the integration by using function int. Gives you a symbolic output of this function, which you can deal further, and we'll see how that works in a moment. If we want to have now numerical values for the integral within specific boundaries, which is very often the case in practical applications like modeling, then we can do the same thing again. We start defining our symbolic variable, define our symbolic function with specific values that are input here from how I wrote it up. And we can, before we actually do it, we can take a look at this function, but you know that we cannot plot symbolic functions. How can we look at this function just how it is before we integrate it? Well, we have to convert it to a MATLAB algebraic function. And here's the command to do it. If we take this function and we apply a function called MATLAB function, then our symbolic function nsim will be converted into a MATLAB function, which I have chosen to be called nmat in this case. Right, so we can execute this piece of code, and we'll get the same thing as before, but now it's available in the form nmat, available for us for example, plotting. And we know how to do plotting, either in the textbook or if you have attended the last support session. If we use fplot to plot this function, we can directly make a graph, and the graph will show us how this function works over a defined limit. In this case, from 0 to 500, the graph is ascending quadratically ascending up to a value of 3,500. And we'll come back to this plot in a second. Right? So now let's look at the integral. Our function was called nsim, so we can integrate this function by applying the function int to it, and we get a symbolic output. If I do this again, chosen here, then we can see the symbolic output is here. That is the integral of the function that we have chosen. Again, we can convert it into MATLAB algebraic function for further plotting, and we can use the same plot as before. I do that quickly in a moment to get our plot by executing this code. Now we have on top the original function and on the bottom the integral of the function. You can hardly see the axis, so I increase the font drastically so you can better see what this is actually showing. And we can see that while the function takes values between 0 and approximately 3,500, our integral grows from 0 to approximately 600,000, 6 times 10 to the power of 5. I highlight our integral by making it a thicker line, and you can see transforming it into an algebraic function makes it easy to have a look via fplot looking at the graph. So this is what we have obtained from the integration of the function. And we can now go further and use this algebraic function, of course, to get specific values. And because the function is the integral already, we can just plug in the values of the boundaries, subtract them from each other, and obtain the numerical value of the integral for specific ranges. So if we are asked to evaluate the integral between 0 and 500, what we have to do, we take the integral at 0.500, and that's the upper border, and subtract from it the integral at the point 0, the starting point, which is the lower border. And we have that numerical value displayed in the command window. Here's our command window. The integral is given here in numerical values as 6 to the power of 10 to 6 times 10 to the 5. So this is the value then that we saw previously in the plot also. Just we had to estimate it, and here's the exact value. That was one way of getting numerical output from the symbolic integrated function. It's actually possible to get directly the numerical output from the symbolic manipulation. And here's how to do it. As before, we have to define our symbolic variable, have to define our function, which is nsim in this case. And then we perform int not only on our function nsim, choosing the radius as a variable or this r as a variable, but we specify separated by commas 0 as the lower limit and 500 as the upper limit. And if this is done correctly, we'll get immediately the symbolic output, the output of the symbolic function, and it says here we have 575,000 times pi divided by 3. So you can guess that the range is already correct, but if this is a formula now, so I have called it MM_FORM. If you would rather like to know what this formula means in actual numerical value, you use a function called eval, that's evaluate. And if you perform evaluate on this function, you will get the true value in just in this form here, 600,000 and 602,140. So that is called the direct method because the symbolic manipulation lets you get the values directly. So we have now seen two methods, both of which can be useful in their way, but you remember that because of the convenience to be able to plot algebraic functions, the conversion into a MATLAB algebraic function is often a convenient way to do. So with this introduction, we finish our part on the integration, and I close the plot of our function and the integral, and we have a short break to get to the second section, which will be on the Michaelis-Menten equation, dealing with it in MATLAB. So we use this first look at the Michaelis-Menten equation in order to, of course, then expand it and get it into the Hill equation, which is our ultimate goal. First thing is we define our Michaelis-Menten function. It's a rate, so I call it V, and define it in a way that has two components. First is those things that may vary during the manipulation of this function, which implies parameters, k, our Menten constant, Vmax, our maximal rate, and variables. For example, here it is the substrate concentration S. Followed this definition of the things that may change during the manipulation is following the actual form of the function, which we see in our text, so often written as Vmax times S divided by k plus S. So this is the simplest form in which it can be written, and if we execute this code, we have within our working space this function V defined. Now we can use this function in order to obtain it for specific sets of parameters. How do we put in these parameters? Well, we take the function V and give as an argument the parameters that we want to specify in the order in which they have been defined. Definition was S first, K second, Vmax third, so that's the way we have to put them. If we put in the second place 0.1, it means that the value for K is specified as 0.1. And the final value, as you can see in that function definition, will be those attributed to the Vmax, to the maximum rate of the function. So in this case, it's set to 10. And we have done this 3 times because we want to see the function for different values of the Michaelis-Menten constant Km. So we have chosen different values. One is 0.1, one is 1.0, and the final one is 10. So different points, different values for the Km constant, and giving us functions v1, v2, and v3 for those specific constants, leaving, however, s as a variable for which we can then obtain our plot. So here's the plot. Let's take a quick look at the commands that we have in order to get this plot complete. First line here is setting the limits. These are the upper and the lower bound of the substrate concentration that we want to have displayed. Second line calls fplot, that's the function plot within those limits that we have just specified in the line before. And we call the function v1, which is the one, if you allow me to go back, function v1 was the one where the Km value was equal to 0.1. So we plot this function first thing, and following these 2 arguments we have within quotes the letter R, meaning that the function will be displayed in red color. And so consecutively we also plot the second function with k equal to the Km value equal to 1, that's in blue, and finally the third function with the Km value equal to 10 specified in the green color. We adjust our axis to values between 0 and 10, both on the horizontal and the vertical axis. We apply a label to the y-axis, to the vertical axis, which is called rate. That's the output of our function. It's a rate, according to Michaelis-Menten. We can plot our variables as an x-label on the horizontal axis. It's the concentration of substrate. And we complete this by giving it a legend where we can have the different graphs annotated so to easier find out which means which. If I display the result of executing this MATLAB code, maybe I first make our axis as before, axis labels larger so we can better see what's going on. And we can see that we have three graphs. If I make the lines thicker, you will be able also to better see them on your display. The red, the blue, and the green, one by one. And you can see how changing the Km constant changes the function for the same range of substrate concentrations. So if you then look at a specific concentration of substrate, say a value of equal to 5, we can then see that for k equal to 10, the rate will be lowest, k equal to 1 will be second, and the highest rate will be obtained for a small value of Km, which is clear because Km value in a sense defines the inverse of affinity for the substrate. So the smaller the value of Km is, the higher the affinity for the substrate and the higher the probability that substrate is being converted into product. That terminates our short exercise on the Michaelis-Menten function. And I suggest, if you like, you can do a further exercise to check whether you have understood this manipulation by trying to rearrange the output such that the rate is plotted not as a function of substrate concentration, but as a function of the Km value. And here's some example code. You can take a look at it and see if you understand it. Best would be if you could first try it for yourself and see whether you can get reasonable output of the rate as a function of different values of k within a certain range. And in this case, I have made 3 plots for different values of the Vmax, which means that this tool is of course flexible enough to show you whatever you want, whichever parameter you want to turn into your independent variable. It depends on you, and you just have to specify it. And you can then have plots of everything against everything if you like. So that's good to ask also further questions, not just the dependence on the substrate, but in this case the dependence of the rate on the Michaelis-Menten constant, which we have just seen in 3 examples, but here's a continuous display if you choose to do this exercise. Plot is also given if you like. You can test it for yourself and see if you are able to follow these instructions. Okay, let's go back to this thing here. The Hill equation defines the rate very similar to the Michaelis-Menten equation. The thing that is really different now is that substrate concentration is taken to a power. And for those who have read a deviation of this equation, it's actually associated, or it was associated by Hill, with the idea that there can be cooperativity, and particularly thinking of protein that are dimeric or tetrameric, where they have multiple units with same functionality, such that a single protein can bind variable substrate molecules at the same time in different locations. Okay, let's take a look at this Hill function. So what is different now? We set it up as before. We define our rate, the things that can change, and our function on the right-hand side. So the one thing that differs now that we have a power, which is a parameter n here, the Hill coefficient, or the Hill exponent if you like. And so we have to add this to the parameters that we want to be able to manipulate further on. Right, our function is slightly modified in that s is substituted by s to the power of n, s to the power of this Hill coefficient. Km, the original dissociation constant, is now substituted with k to the power of n. And finally also this s down here in the denominator substituted by s to the power of n. So this is just the Hill equation as we saw it defined and as it's in the textbook. So we execute this piece of code here to get that into the working space. We have now our algebraic function, and of course for this function, as before, we can produce output for different sets of specific parameters that we are interested in. So what is happening here is you can see that s, the first argument of the function, is our variable that will be displayed on the horizontal axis. 1 is the value, if we just go back to the function, for k. So our km, or Menten constant, is now equal to 1. Maximum rate is equal to 10. Vmax equal to 10 in all cases. And the thing that changes is the exponent. The first example, exponent is set equal to 1, which means Hill equation is reduced to the Michaelis-Menten equation. It is the Michaelis-Menten equation. Second case, n is chosen as 2. That's quadratic now. So we already have a divergence from the Michaelis-Menten equation. And the third example is then an even higher exponent with a value of 5. It's a more drastic effect to show how the Hill function with an exponent larger than 1 deviates from the original Michaelis-Menten where the exponent was equal to 1. Right, let's execute this piece of the code. See, it has happened already, and I have, very similar to what we did before, defined our plot output. So we have a few labels here, and we can see our functions. I make the graphs a little bit thicker again, so we can see nicely our 3 graphs, one in green, one in blue, one in red. Which one is the Michaelis-Menten one? Well, the legend actually tells us. If I make it bigger, maybe you can also read it. The red graph is the Michaelis-Menten one with the exponent set equal to 1. So that's our hyperbolic function as we know it from before, and no surprise here. What we now have is, in addition, the blue graph. That is an exponent which is larger than 1. And you can see a slight sigmoidal shape, meaning starting slow at the beginning, so the blue graph stays below the red curve, means the rates for small substrate concentrations are less than the Michaelis-Menten one. But beyond a point for substrate concentration, in this specific case values larger than 1, the blue graph will be above the red graph, meaning that the rates for the same substrate concentration will be higher in the cooperative case compared to the non-cooperative case. And in the green case here with n equal to 5, you can see the same thing more drastically. It's a clear sigmoid now, a so-called switching function, one function that goes from a range of s where there's very small values to a range of s where there's maximal values with a fairly steep rise in between. So this is a good look at how the Hill function, the Hill coefficient now, the Hill exponent, changes the shape of this function and how rates differ on either side of this special point here, in this case s equal to 1, where all functions meet. And we'll have a look at this special point in a minute. Okay, for the moment I close this label. And what we're now going to do is to have a little bit of a mathematical look at this Hill function. In order to do this, I'm going to clear my control window, and I'm going to take the Hill function and plug it into my window such that you can see it nicely. Just a second, yes. So you can see this is our Hill function as we have just seen it. And what we're going to ask is, how does it behave in the extremes of either very large substrate concentrations or very small substrate concentrations? Let's go first to the case of very large substrate concentrations. What does it mean if substrate concentration is very, very large? I mean, very, very large. Then in a sum compared to a constant that is not changing, this substrate concentration will be dominant. So means this constant can actually be skipped. We can just take it away, because for very large values of s to the power of n, we will have a dominance so drastic that this can be approximated by just taking s to the power of n and ignoring the other constant. Now if we look at this function that remains, we can see that what we are doing here is s to the power of n in the numerator, and it's divided by s to the power of n. But this is just 1. S to the power of n divided by itself is just equal to 1. So we can substitute it with the value 1. So what we see here, multiplication by 1 doesn't change its value. For very large substrate concentrations, the rate according to this Hill equation will be V max, means it will be identical to the rate that we had obtained in the case of the Michaelis-Menten function. In either case, the limiting rate for large substrate concentration will be the same. Right, now let's look at the other case. Let's look at the case where s to the power of n is very, very small. Now for a given constant that is unchanging, k to the power of n, if s is very, very small compared to this constant, we can now eliminate this additive term here, which is negligible. So we assume that a good approximation to this function is actually to just say the denominator is equal to k to the power of n. And if we have this, we can see that we have now a new function which depends on Vmax times s to the power of n as before, but is divided now only by k to the power of n. So what will this function look like? Maybe you know already, but we can also take a look and plot this function. Right, so what I've done here in this exercise, which is further down the code, which is called approximation for small s, I have taken what I have just derived in the command window and, as before, defined my rate with this modified function. So rather than having the complete Michaelis-Menten function, we have here the simplified equation, the simplified Hill equation, which is Vmax times s to the power of n divided by k to the power of n. And if we treat it just in an analog way as before, we can look at the graph of this function similarly for different values of n, just as we did before. So we define 3 specific functions and we use values as before of 1, the case of where it reduces to the Michaelis-Menten. We use 2 for the quadratic case, and we use 5 for a more drastic Hill case. So if I execute this function here, we can see the output of this plot. But what we can do now, before going further, we can now substitute, just a second, we can now substitute this and have both plots, the original and the simplified, plotted on top of each other. Now that looks very confusing, so we take a look at the Michaelis-Menten first, so I eliminate all those things that were not there. The Michaelis-Menten function given is then shown here by the thick red line, and I compare it to the approximation that we get for small values as we have just executed it in the dotted line. Make it a dotted line, then you can easier see it. So the dotted line is the straight line here, and we can see that indeed these two functions differ very widely, apart from the section near the origin where they coincide nicely. So we can see that for a certain range of substrate concentration, these two functions do coincide, but it's only, as we have assumed, for small values of S. Now if we take this away, let's take a look at the opposite case of the Michaelis-Menten, of the Hill function. What does it look like if we have it very thick? Here's our approximation. Just a second, I can't see it. Take a look at our Hill function. If it's there, it doesn't show up. I'm not so sure why. I just have to, sorry, I might have to do it again. So I plot this function again. Take this out, plot our function again, and put on top of it our approximation. So we now want to have a look at how is the Hill function approximated by our simplification. Let's first take a look at the Hill function. Here's the Hill function, what the sigmoid in a close-up view. And if we now look at our approximation that we have received for small values, you can see that indeed, again, for values of S that are very small, these functions coincide quite nicely, but they do deviate from each other as S goes larger. If we do the same thing now and compare also the values for the larger exponent, you can see a certain trend here. Namely, you can see that the Hill function that we can see here is being approximated by our simplified function, but to a much larger extent than the original Michaelis-Menten function. So you can see in this case we have a fairly good coincidence of these two functions for higher values of S compared to the previous approximations. Nevertheless, the simplification is just that. It's a simplification, it's an approximation, and we can only describe part of the function completely. So this shows that we have some ways of looking at specific cases by doing these approximations, large S or small s. We can understand already some features of the function and can then try to compose a complete understanding by putting this into one overall picture. Right, this concludes our session here looking at the Hill function using fplot, and we are now ready to do a slightly more complicated example which we have in MATLAB code, which is in the third file that has the starting name A6. And we want to now do a complicated example where each step in itself might not be so complicated, but it's overall complicated. So I'll try to go through it in a fairly slow fashion. We want to take a look at the Hill function and the features of the Hill function as we have just seen it before. And specifically, we want to take a look at the differentiation at the first and the second derivative of the Hill function, finding out what else it can tell us about the function in addition to what we already know. So I start by clearing my screen, and I use the symbolic toolbox for variables in the Hill function, and I define my Hill function, as you can see here, as Vmax times s to the power of n divided by s to the power of n plus k to the power of n. Same as before. So we can execute this piece of code and get our Hill function as a symbolic with the name Hill. The differentiation of this function symbolically is done with the function called diff, D-I-F-F, and we have to specify the function that we want to use. In this case, we will use Hill, the Hill function, and we will differentiate with respect to the substrate concentration S. So executing this piece of code here, we get an expression that is a fairly large fairly large symbolic expression containing S, Dmax, N, and K as symbolic variables. We can try to use this code to simplify the expression if possible. There's no guarantee that it will help, but it might help a little bit if we apply this line simplify and maybe do it again for only this section. Then we get an expression in the command window which shows us, well, it's something that you get by applying the quotient rule, and you will not be surprised if you do it by a pencil on a piece of paper. You will get a similar result after some reorganization of the output. So we have a symbolic representation of first order derivative of this equation. What we can do now is we can, of course, take a look at those two, and we know how to do that. If we want to take a look at symbolic functions, we must first convert them to algebraic functions, to MATLAB functions, as they are called. So using this command on both Hill, which is the original Hill function, and on the first order derivative, which is dHill, derivative of Hill, we can then get algebraic function, which I have now labeled with the letter N for MATLAB in the beginning, which we can use to plot them graphically. You remember, for graphic plotting, we need to input specific values of parameters. We do this here just in the way as we did before. For the function, executing this piece of code gives us f1 and f2, gives us meaningful ways to use fplot to get a graph of this. I don't go into the detail of the graphic. It's similar to before, but you need to look in detail at it in order to understand it. If I execute it here, I get a window with two plots, where on top we have plotted the original Hill function, and below it we have plotted the first derivative. So I just choose my title so you can see it slightly better, making it larger. So we can see the Hill function in red here, and we can see the first derivative below also plotted in red, and can already guess that there's a very specific point that interests us, of course, namely the Hill function has an inflection point. And what will an inflection point look like? In the first derivative, it will be a maximum. The first derivative will have a maximum at the inflection point of any function. Right? So it's fairly straightforward so far, but we will now take it further. In order to find out where actually is this inflection point, we are going one step further. We're not looking at the first derivative, we're actually looking at the second derivative. How do we get the second derivative? We now use the function diff, differentiating over function, and we apply to the first derivative, meaning differentiating the differentiated function, getting the second derivative. In conjunction with the simplify command, and take a look what that looks like. And I do it again so you can see what does it look like. It's a fairly big expression. It's a very complicated expression already, but we can now take a look at what this second derivative looks like after we have converted it into an algebraic function. So I've done that with the same function, MATLAB function, as before, and we get the result. If we now produce a function for the same parameter values as before and plot it in this code, we get a third window with our second derivative plotted. I urge everybody to go through it step by step and to try to also do this for other functions. As you can see, we have now a possibility to check the function original, the first derivative, and the second derivative at the same time. And I want to use the last part of our session to show that we can actually solve from looking at the second derivative. We can find out what this inflection point of the original Hill function is. You can guess it might be roughly somewhere between 0 and 1 in terms of substrate concentration, and we can see it from the maximum similarly if the first derivative, but we have now a very nice feature. In the second derivative, the inflection point becomes 0. That means we can actually find out where is this point, where is this function 0, if we solve this function algebraically. So to solve a function algebraically, to solve the function symbolically, before we do it algebraically, solve it symbolically, we use the function solve and we apply it to our second derivative. That will find out where, with respect to the substrate concentration, this function is 0. So we execute this code. So take this away. Execute this code, and we get an explicit formula for the inflection point. So at this point, where S inflect substrate concentration of the inflection point follows this formula, which depends on K and N. The values of K and N determine where the inflection point lies. Interestingly, as you might observe here, we don't have any dependence on Vmax, on the maximum rate of our function. So now comes the difficult part. We want to find out what is the numerical value of the substrate concentration where the inflection point lies. So in order to do that, we use a function called subs for substitute. We can now use our knowledge of the inflection point, namely S inflect. This is our inflection point given explicitly as you see in the control window. And we want to have that substituted into our Hill function by assigning specific values of K, V, max, and N, and getting a result. So for specific values of K, V, max, and N, the substitution function subs allows us to get an explicit expression for how big is the substrate concentration for the inflection point of the original Hill function. And you can see it's some term. It's 3 to the power of 1 over 2, so that's the square root of 3, and it's divided by 3. If we actually want to see the value, the numerical value, we use eval, evaluate. And if we execute evaluate, we get the numerical value. It's shown as 0.5774. So for a substrate concentration of 0.5774, we will have the rate of the Hill function at which there's an inflection point. And to complete this, we can now substitute this value that we have found, the inflection point substrate concentration, into the original Hill equation. If you still remember, our original Hill equation was called Hill, and we can substitute the value that we have found, which is our 0.577, the numerical value, into this Hill equation, and we can find out what is the Hill function at this point. And if you use this code and execute it, the Hill function, the rate at this point of substrate concentration will have the value of 2.5. So I've done it both here. I have a term here, so to speak, a formula, and I have the numerical value calculated by using the eval function as before. So I know this is not a quite a straightforward function, but it's worth it going through it step by step, defining the original function. I'll show us the plot, defining the original function, looking at the first derivative in order to see inflection points as maxima, looking at the second derivative in order to see inflection points as zero crossings, and then use the the substitute functionality of MATLAB to get the specific values of both horizontally the substrate concentration and vertically the explicit rate at this point. And if you want, you can also execute the last code, which does nothing but put a line at the point where we have found this value. And if I make it slightly larger, you can see that for this value we have a line, and this line actually coincides with the maximum of the first derivative and with the zero crossing of the second derivative. This concludes our exercise on dealing with various functionalities with the Hill function to find out about any of its features actually. And we have looked at the function, at function plots, at specific values, at specific limitations for approximative values, and at specific features like the inflection point in this case. So mathematically, it's actually possible to do this for any function if you have understood how to do it for this function here. So that should be transferable now. If I clear my command window and bring up that concludes our discussion of the Hill function. Hopefully helps you to complete your assignments on time. And I skipped this flow model. That was a suggestion. If you want to download the code, which is on the material side, you can actually try to simulate a model reaction as it might work in vivo if the enzyme kinetics is cooperative. So I don't go into the detail here, but what I want to mention is that if you then want to go into simulating a model for a specific enzyme, you will need to know the values. It's shown here on this graph as, for example, Vmax, the maximum rate, K, the constant, the Michaelis-Menten constant, and N, the Hill coefficient or Hill exponent. Where do you get those values from if you need them? So this is just a recommendation. A very well curated database that answers these and similar questions about enzyme kinetics, and that is very helpful for setting up a model, is the Sabio RK. So the link is given in this slide here. Is it possible? Can I just click on it? Sabio RK, and I just show this is the web page how you get on it if you click the link. So you will get to the Sabio RK database. But we don't do it. I have a section here, a selection of text that you get if you do a search for hexokinase in the human. I have actually should do that. I wanted to highlight it here. So I have made a search for hexokinase in the human pancreatic beta cells. And where do you get those values from? So I'll show you where the formula is. The formula is somewhere here. It's actually a Michaelis-Menten derivation. It's a Hill function. So we need to know Vmax and K and N for the value, but these are all given here. So you can find them looking closer at this graph. It's not very big here, so you need to go to the web page. You can get those values and work with them. What you have to be careful is that they are not given as Vmax as we have used it, but there's actually one thing to be careful to look at the units. It's actually given as specific activity of the enzyme, so you need to convert it before you can use it in the model. With this recommendation of using the Sabio RK web database, we conclude our session for today. And we hope that you have had some useful information into getting flexible